You use a microwave oven, on average, about 5 times a day. You press a button, things get hot, and you do not think about it. But here is a question almost nobody asks. Why does food get hot inside a metal box that itself stays cool? That is not how heat works. Heat is supposed to move from a hot surface to a cold thing. Your oven gets hot. Your stovetop gets hot. Your campfire gets hot. But a microwave? The walls do not heat up. The glass plate barely warms. The air inside stays cool. Only the food gets hot. And somehow, it gets hot from the inside out, which, if you think about it for more than 3 seconds, is genuinely strange. Because the answer to how this works involves a classified military weapons program, a self-taught engineer with a grade school education, a melted chocolate bar in a trouser pocket, and a technology so fundamentally alien to cooking that the public refused to trust it for nearly 3 decades. This is the secret history of the microwave oven, and I promise you, it is one of the weirdest invention stories in the 20th century. If you enjoy these deep dives into the hidden engineering behind everyday objects, hit subscribe. We release a new episode every week, and you will never look at your kitchen the same way again. To understand the microwave oven, you first need to understand the magnetron. And to understand the magnetron, you need to understand a very specific military problem from 1940. Britain was losing the war. German bombers were crossing the English Channel at night, and Britain's early radar systems could detect them, but not accurately enough. Radar works by sending out radio waves, bouncing them off objects, and measuring the return signal to calculate distance and direction. The problem was wavelength. Britain's existing radar used long radio waves, sometimes 10 meters from peak to peak. Long waves can detect large objects at great distances, which is useful, but they produce blurry images. Imagine trying to photograph a housefly with a camera that can only focus on things the size of a car. You know something is there. You have no idea what it is or exactly where it is. What Britain needed was short-wavelength radar. Microwaves. Waves measured in centimeters rather than meters. Centimeter wave radar could pinpoint individual aircraft, track them through clouds, and eventually guide anti-aircraft fire with lethal precision. The catch was that nobody could generate microwaves with enough power to be useful. This is where 2 physicists at the University of Birmingham enter the story: John Randall and Harry Boot. In February of 1940, working in a basement laboratory with virtually no funding, they built a device called the cavity magnetron. The basic idea was not entirely new. Magnetrons had existed in crude forms since the 1920s. But Randall and Boot's version was radically different. They took a solid copper block and drilled cylindrical cavities into it, arranged in a circle, like the chambers of a revolver. A cathode sat in the center. When high voltage was applied and a magnetic field was introduced perpendicular to the electric field, electrons spiraling outward would sweep past the cavity openings and set up resonant oscillations. The cavities acted like tiny tuning forks, each one reinforcing the others, producing coherent microwave radiation at enormous power levels. Their first prototype, small enough to hold in one hand, generated 400 watts at a wavelength of 9.8 centimeters. This was roughly 100 times more powerful than any existing microwave source. It was, without exaggeration, one of the most important inventions of World War II. The cavity magnetron was so valuable that the British government made a fateful decision. In September 1940, Sir Henry Tizard led a secret mission to the United States, carrying a black metal deed box containing, among other things, a single cavity magnetron. The goal was to share Britain's most advanced military technology with American industry in exchange for manufacturing capacity. The Tizard mission is sometimes called the most valuable cargo ever brought to American shores. The magnetron was handed to the Massachusetts Institute of Technology, where it became the basis of the Radiation Laboratory, a sprawling secret research facility that would eventually employ 4,000 people and develop radar systems that helped win the war. But the actual manufacturing contract went to a company in Waltham, Massachusetts, called Raytheon. Raytheon was, at the time, a mid-sized electronics firm that made vacuum tubes. They won the magnetron production contract largely because of one man, Percy Spencer. Born in Howland, Maine, in 1894, Spencer had almost no formal education. His father died when he was an infant. His mother left shortly after. He was raised by an aunt and uncle, and the uncle died when Spencer was 7. He never finished grammar school. At age 12, he went to work in a spool mill. At 14, he helped wire one of the first hydroelectric plants in his area, teaching himself electrical engineering by reading everything he could find. He joined the Navy at 18, taught himself trigonometry, calculus, chemistry, physics, and metallurgy, while serving as a radio operator. After the war, he joined Raytheon and rose through the ranks purely on the strength of his self-taught expertise. By 1940, Spencer was one of the world's leading experts on magnetron design and manufacturing. He did not just oversee production, he fundamentally redesigned the manufacturing process. When Raytheon received the British magnetron, they were producing about 17 tubes a day using precision machining. Spencer studied the device, rethought the production methods, and introduced techniques that increased output to 2,600 tubes a day. That is not a typo. He improved production by a factor of roughly 150. Raytheon went from a minor subcontractor to the primary magnetron supplier for the Allied war effort, producing about 80% of all magnetrons used in the war. Spencer received the Distinguished Public Service Award from the Navy, the highest honor the department gives to civilians. And he did all of this without a high school diploma. Now, the chocolate bar. The story has been told so many times that it has acquired a mythological quality, but the core facts are well documented. Sometime in 1945, with the war ending and Raytheon looking for peacetime applications for its magnetron technology, Percy Spencer was standing near an active magnetron test set. He noticed that a peanut cluster bar in his shirt pocket had melted. This was not the first time someone had noticed that magnetrons generated heat. Engineers working with radar equipment had been warming their hands near magnetron waveguides for years. The difference was that Spencer did not shrug it off. He stopped. He thought about it. And then he did something that separates great engineers from good ones. He tested it. The next morning, Spencer brought in a bag of popcorn kernels. He placed them near the magnetron. They popped. They scattered all over the laboratory floor. This was exciting, but inconclusive. Popcorn pops because of internal water pressure, which builds as the kernel heats up. Spencer needed to understand whether the microwaves were heating water specifically. So he tried a more controlled experiment. He took an egg and placed it near the magnetron. The egg exploded. Hot yolk sprayed everywhere, reportedly hitting a colleague in the face. This was messy, but scientifically informative. The egg had heated from the inside out. The water molecules inside the egg absorbed microwave energy faster than the heat could dissipate through the shell. Internal pressure built until the shell failed catastrophically. Spencer now had a hypothesis. Microwaves at the frequency produced by the magnetron, roughly 2.45 gigahertz, were being selectively absorbed by water molecules in food. He was right, and the physics are genuinely elegant. A water molecule is polar. It has a slight positive charge on one end and a slight negative charge on the other, like a tiny bar magnet. When you expose water molecules to an oscillating electromagnetic field at 2.45 gigahertz, those molecules try to align themselves with the field. But the field reverses direction 2.45 billion times per second. The molecules cannot keep up. They rotate, jiggle, and vibrate as they try to follow the oscillating field. This molecular friction generates heat. The microwave energy is not cooking the food in any traditional sense. It is making the water molecules inside the food vibrate so intensely that they heat up their surroundings through friction. This is why dry foods barely heat in a microwave, why ice is slow to melt in one, and why a ceramic plate can come out cool while the soup on top of it is scalding. The microwaves pass through ceramic, glass, and plastic. They reflect off metal, and they are absorbed almost exclusively by water, fats, and sugars. Spencer filed a patent on October 8, 1945. The patent, number 2495429, was titled Method of Treating Foodstuffs and was assigned to Raytheon. It described a process of directing microwave energy into a metal cooking chamber. The key innovation was the enclosure. Without a metal box to contain and reflect the microwaves, the energy would scatter in all directions. The metal walls bounce the microwaves around the interior, creating a complex standing wave pattern that ensures the food is exposed to energy from multiple angles. Spencer understood that the box was not just a container. It was a resonant cavity, a larger version of the same principle that made the magnetron work in the first place. Cavities within cavities. Radar technology literally wearing a kitchen apron. Raytheon introduced the first commercial microwave oven in 1947. They called it the radar range. And it was, by any consumer standard, completely absurd. It stood nearly 6 feet tall. It weighed about 750 pounds. It required a dedicated 220-volt electrical line and a water cooling system for the magnetron. It consumed 3,000 watts of power, and it cost approximately $5,000, which in 1947 money is equivalent to roughly $68,000 today. This was not a kitchen appliance. This was an industrial installation. Raytheon marketed it to restaurants, railroad dining cars, and ocean liners. The first radar range was installed on a ship, the nuclear-powered passenger cargo vessel NS Savannah, and in the galley of a restaurant in Cleveland. Sales were modest. The public had no idea what to do with it, and restaurant chefs were skeptical. Why would you need to heat food in seconds when your kitchen is already designed around processes that take minutes? The radar range spent nearly 2 decades as a commercial curiosity. Raytheon kept improving the technology. They shrank the magnetron, improved the power supply, and eliminated the water cooling requirement by switching to air-cooled magnetron designs. But the fundamental problem was not engineering. It was perception. The public associated microwaves with radar, and radar with warfare, and warfare with danger. The word radiation appeared in every description. And although microwave radiation is non-ionizing and fundamentally different from nuclear radiation, the distinction was lost on most consumers. People were afraid of it. They imagined invisible beams leaking through the door, cooking their internal organs while they waited for leftovers. This fear was not entirely irrational. Early magnetrons did produce some radiation leakage, and safety standards were still being established. But the fear far exceeded the actual risk. The breakthrough came in 1967, and it came from an unlikely direction. Raytheon had acquired Amana Refrigeration in 1965, primarily because Amana had something Raytheon lacked: a consumer brand and a nationwide distribution network for kitchen appliances. In 1967, Amana introduced the radar range countertop model. It was the first microwave oven designed specifically for home use. It plugged into a standard 115-volt household outlet. It sat on a kitchen counter. It weighed under 100 pounds, and it cost $495, which is roughly $4,500 in today's money. Still expensive, but no longer absurd. More importantly, it looked like a kitchen appliance rather than a piece of military equipment. Amana deliberately designed it with rounded corners, a wood grain panel, and a conventional-looking control dial. They were not just selling a cooking device. They were selling normalcy. But the public remained wary. Throughout the late 1960s and early 70s, microwave oven sales grew slowly. Consumer Reports tested them and gave cautious, equivocal reviews. Nutritionists questioned whether microwaved food retained its vitamins. Environmentalists raised concerns about energy consumption. And a persistent urban legend claimed that microwaves destroyed the molecular structure of food, rendering it nutritionally dead. None of this was supported by evidence. Microwaving actually preserves more vitamins than boiling, because food spends less time at high temperature and is not immersed in water that leaches nutrients. But facts rarely win against fear, especially when the fear involves invisible energy and the word radiation. There is something worth pausing on here. The gap between invention and adoption for the microwave oven was not a technology problem. It was a trust problem. And trust problems are harder to solve than engineering problems because you cannot fix them with better components. You fix them with time, familiarity, and changing circumstances. Raytheon could build a better magnetron every year. They could not make people less afraid of invisible cooking energy. The company tried everything. They ran advertisements showing smiling families using the radar range. They placed demonstration units in department stores. They hired home economists to develop microwave recipes and publish cookbooks. None of it worked particularly well. The demonstrations were almost counterproductive. Watching food heat up without any visible source of heat, no flame, no glowing element, no hot surface, was unsettling to many observers. It looked like magic, and magic in the kitchen made people nervous. One Raytheon engineer reportedly said that selling the microwave to consumers was like trying to sell an invisible stove. The technology worked perfectly. The problem was that people could not see it working. And what you cannot see, you do not trust. What finally turned the tide was not a scientific study or a marketing campaign. It was demographics. By the mid-1970s, the number of dual-income households in America was rising sharply. More women were entering the workforce full-time, and the traditional model of one parent spending hours preparing meals was becoming economically impractical for millions of families. People needed to cook faster. They needed to reheat leftovers. They needed to defrost frozen meat at 6:30 in the evening because nobody had remembered to take it out of the freezer that morning. The microwave oven was not a luxury gadget. It was a time compression machine. And time was exactly what dual-income families did not have. Sales began climbing in 1975 and accelerated through the early 80s. And here, a second force entered the picture: Japanese manufacturing. Sharp, Sanyo, Panasonic, and Toshiba had been watching the American microwave market for years. Japanese electronics manufacturers were already masters of miniaturization and cost reduction from their work in transistor radios and television sets. They applied the same discipline to microwave ovens. By the late 70s, Japanese manufacturers were producing compact, reliable microwave ovens at price points that undercut American models by 30 to 50%. A Sharp countertop model in 1979 cost under $300. Suddenly, the microwave was not a major household purchase. It was an impulse buy at Sears. The combination of demographic need and falling prices created a feedback loop. More households bought microwaves, which increased production volume, which drove costs down further, which made them accessible to even more households. It was the same adoption curve that had played out with television sets 2 decades earlier, compressed into half the time. Meanwhile, Litton Industries, which had entered the market in the late 60s, introduced models with rotating turntables, which solved the uneven heating problem caused by standing wave patterns inside the cooking chamber. Before turntables, you had hot spots and cold spots. The standing waves meant that some locations inside the oven received intense energy, while others received almost none. Food sitting in a cold spot would stay raw, while food in a hot spot overcooked. The turntable moved the food through different positions in the standing wave pattern, averaging out the exposure. It was an elegant mechanical solution to a complex electromagnetic problem. And it is the reason your microwave has a glass plate that spins. That spinning plate is not decorative. It is compensating for a fundamental limitation of how microwaves distribute energy in a rectangular metal box. By 1986, roughly 25% of American households owned a microwave. By 1990, the number exceeded 75%. By 2000, it was over 90%. The microwave oven went from military radar technology to universal kitchen appliance in about 40 years. But the speed of adoption concealed a deeper question that the food industry was scrambling to answer. What do you actually cook in a microwave? The answer, it turned out, was almost nothing. Not from scratch, anyway. The microwave excels at reheating and defrosting. It is mediocre at cooking raw food. The reason comes back to physics. Microwaves heat water, but they do not brown food. Browning, also called the Maillard reaction, requires surface temperatures above about 140 degrees Celsius. Water boils at 100 degrees Celsius. As long as the surface of your food contains water, the microwave will drive that surface temperature toward 100 degrees and hold it there, because the water evaporates and carries away heat before the temperature can climb higher. This is why microwave-cooked meat looks gray and unappetizing. Why microwave bread turns rubbery instead of crusty. Why you cannot make toast in a microwave. The machine is fundamentally incapable of producing the dry, high-temperature surface conditions that create flavor through browning. The food industry responded by engineering foods specifically for microwave preparation. Microwave popcorn, introduced commercially in 1981 by General Mills, used a susceptor, a thin metallic film laminated onto the inside of the bag. The susceptor absorbs microwave energy and converts it to direct heat, reaching temperatures high enough to pop the kernels and produce browning. Hot Pockets, introduced in 1983, used a similar susceptor sleeve. Lean Cuisine, Stouffer's, and dozens of other brands redesigned their frozen meals around microwave heating times and standing wave patterns. The little cardboard sleeve your frozen burrito comes in is not just packaging. It is a microwave interaction device engineered to modify how electromagnetic energy reaches the food surface. Meanwhile, the engineering of the oven itself was evolving in ways most consumers never noticed. The door is perhaps the most sophisticated component. A microwave oven door must do two contradictory things. It must be transparent to visible light, so you can watch your food. And it must be completely opaque to microwaves, so the energy stays inside the box. The solution is the perforated metal screen embedded in the door glass. Those tiny holes, typically about 1 millimeter in diameter, are much smaller than the wavelength of the microwaves, which is about 12.2 centimeters. The microwaves see the perforated screen as a solid metal wall and bounce off it. Visible light, with wavelengths measured in hundreds of nanometers, passes through the holes easily. The screen is essentially a frequency-selective filter. It blocks one part of the electromagnetic spectrum while transmitting another. And it does this so effectively that the radiation leakage from a modern microwave oven, measured at 5 centimeters from the door, is typically less than 1% of the level that would be considered remotely hazardous. The safety interlock system is another quietly brilliant piece of engineering. Every microwave oven sold in the United States has at least 2 independent safety interlocks and 1 monitoring switch. If you open the door, the primary interlock cuts power to the magnetron within milliseconds. If the primary interlock fails, the secondary interlock cuts power independently. And if both interlocks fail, the monitoring switch creates a deliberate short circuit that blows the internal fuse, permanently disabling the oven. The system is designed so that no single component failure can result in the oven operating with the door open. This is why you cannot defeat the door switch and run the oven with the door open. The monitoring switch is specifically designed to destroy the oven rather than allow unsafe operation. It is a self-destruct mechanism in your kitchen, and it has probably never crossed your mind. There is one more piece of the microwave's evolution that deserves attention, and it is the part you interact with most directly: the control panel. The original Amana Radarange had a single mechanical dial. You twisted it to set the cooking time, and it ticked down like a kitchen timer. Simple, intuitive, and almost impossible to misuse. But by the early 1980s, manufacturers began replacing mechanical dials with electronic touchpads. This was partly a cost decision. A membrane keypad with printed buttons is cheaper to manufacture than a precision mechanical timer. But it was also a marketing decision. Rows of buttons and a digital display looked modern. They looked like the future. They made a microwave look like it belonged in the same kitchen as a VCR and a programmable coffee maker. The problem was that nobody used any of the buttons. Studies conducted in the 1990s found that the average microwave owner used exactly 3 functions: time cook, defrost, and the number pad, the auto reheat, the sensor cook, the multi-stage programming, the convection combo modes on high-end units. All of these went unused by the vast majority of owners. The average microwave today has more buttons than a television remote and less user comprehension than a tax form. It is a textbook case of feature creep in consumer product design, where marketing departments add capabilities because they look impressive on a spec sheet, not because anyone asked for them. Your microwave almost certainly has a popcorn button. Have you ever pressed it? Does it work well? The answer, statistically, is yes and no, in that order. The modern microwave oven is a remarkably standardized object. Almost every home microwave in the world operates at 2.45 gigahertz. This is not because 2.45 gigahertz is the optimal frequency for heating food. It is a regulatory artifact. The frequency was designated as an ISM band, an industrial, scientific, and medical band, by international agreement. ISM bands are frequencies set aside for non-communication uses, where some radio interference is tolerated. 2.45 gigahertz was available. It was close enough to the water molecule resonance to work well, and it did not interfere with critical communication systems. If the ISM allocation had been different, your microwave might operate at a completely different frequency. Incidentally, 2.45 gigahertz is also the frequency used by Wi-Fi and Bluetooth. This is not a coincidence. Those technologies also use ISM bands, which is why running your microwave can sometimes interfere with your wireless router. They are literally using the same frequency. Your microwave and your laptop are electromagnetic siblings. Here is something else you probably have not considered. The magnetron in your microwave is, functionally, the same device that Randall and Boot built in that Birmingham basement in 1940. Yes, modern magnetrons are smaller, cheaper, and more reliable. They are mass-produced in Chinese and Korean factories for about $5 apiece. The copper block has been replaced by cheaper alloys. The permanent magnets are neodymium instead of the original ferrate. But the operating principle, the resonant cavity design, the electron spiraling mechanism, has not changed in over 80 years. You are heating your soup with a device whose fundamental physics was invented to shoot down German bombers. The same technology that helped win the Battle of the Atlantic is reheating your leftover pasta. Military technology rarely ends up this domestic. And Percy Spencer? He received no royalties from the microwave oven. His patent was assigned to Raytheon, as was standard for employee inventions at the time. He received a $2 bonus. That is not a joke. Raytheon's policy was to give inventors a token bonus when a patent was filed. Spencer continued working at Raytheon, eventually becoming a senior vice president and a member of the board of directors. He held 350 patents by the time he retired. He died in 1970, 3 years after the Amana countertop model made the microwave a household appliance. He lived long enough to see his invention begin its transformation from industrial curiosity to kitchen standard, but not long enough to see it reach 90% of American homes. There is a peculiar irony in the microwave oven's history that I think deserves a moment of reflection. The cavity magnetron was arguably one of the most consequential weapons of World War II. It enabled precision bombing, anti-submarine warfare, and night fighter operations that shifted the balance of the entire conflict. Hundreds of thousands of people died as a direct result of radar-guided weapons made possible by the magnetron. And the same device, the exact same physics, the same resonant cavity design, now sits in virtually every kitchen on Earth, warming milk for babies and reheating soup for office workers. Swords into plowshares does not even begin to cover it. This is swords into soup warmers. It is one of the most dramatic civilian repurposings of military technology in human history. And you use it every day without a second thought. Next time you press that start button and hear the hum of the magnetron spinning up, consider what you are actually hearing. You are hearing a direct descendant of the device that helped win World War II. You are hearing electrons spiraling through resonant cavities, generating electromagnetic waves at 2.45 billion cycles per second. You are hearing those waves bounce off metal walls, pass through glass and ceramic, and be absorbed by water molecules in your food, making them vibrate so furiously they generate heat through friction. You are hearing 80 years of physics, engineering, manufacturing, marketing, fear, skepticism, demographic change, and regulatory compromise, all compressed into a 60-second countdown and a beep. Your microwave oven is not just a kitchen appliance, it is radar technology wearing an apron. And it changed how the entire world eats.